Hi everyone, a warm welcome to my channel. In this video, I am going to illustrate how to find residue at poles. Suppose A is a singular point of f z. Really, residue of f at A is the coefficient of 1 by z minus A in the Lorentz series expansion of f z, whether A removable or pole or essential. But in the case of only poles, we have ready-made equations for finding residues. Now you can watch the very useful results for finding residue at poles. Result number 1. If A is a simple pole of fz, a residue of f at A is limit z tends to A, z minus A into fz. Result number 2. If A is a double pole of fz, residue of f at A is limit z tends to A, first derivative of z minus A the whole square into fz. Result number 3. In general, if A is a pole of order n, residue of f at A is 1 by n minus 1 factorial limit z tends to A n minus 1th derivative of z minus A the whole raised to n into fz. I repeat, you can apply these results only for poles. If the singularity is not a pole, you can find its corresponding residue from its Lorentz series expansion. In this video, I would like to do problems based on simple and double poles. Let me illustrate how to find the residue of a given function through a few functions. So consider the function z plus 1 by z square into z minus 3. Here clearly 0 is a double pole and 3 is a single pole. See, these are the results for or equations for finding residue of the function at a single pole and residue of the function at a double pole. Among these two equations, the equation for finding residue at the single pole is more easier than for finding at the double pole. So in questions, first you find the residue at the single poles, after that you can calculate the residue at the double poles. Here, 3 is a single pole and 0 is a double pole. Let f z equal to z plus 1 by z square into z minus 3. Let me calculate a residue of f at 3. And it is denoted by residue of f at 3. Since it is simple, its equation is the first equation. It is limit z tends to A, z minus A into fz. Here, A is 3. So, limit z tends to 3, z minus 3 into fz. Fz is z plus 1 divided by z square into z minus 3. Next, you evaluate this limit that will give the residue of f at 3. While evaluating, we have to depend on L'Hospital's rule. For avoiding L'Hospital's rule, here you make a cancellation. In almost all questions, in 90% of the functions, you can make a cancellation here so that you can directly find its limit without using L'Hospital's rule. So it is limit z tends to 3, z plus 1 by z square. You put z equal to 3. You can see numerator is 4 and denominator is 9. And see, this is the residue of the given function at 3. Next, residue of f at 0. Since 0 is a single pole, we have to use second result. And it is limit z tends to A d by dz of z minus A the whole square fz. Here the double pole is 0, that is A is 0, so limit z tends to 0, first derivative of z square fz. You replace fz and make a cancellation, then you take its derivative. After getting the derivative, you can evaluate the limit when z tends to 0. So it is limit z tends to 0, d by dz of z square into z plus 1 by z square into z minus 3. We can remove this 3 and it is limit z tends to 0, d by dz of z plus 1 by z minus 3. Next we have to find the first derivative of that function. See, it is a quotient, so you have to apply the quotient rule. Limit z tends to 0, derivative of u by v, quotient rule. It is denominator square upon denominator into derivative of the numerator minus numerator into derivative of the denominator. So limit z tends to 0, denominator square upon denominator into derivative of the numerator with respect to z, which is 1 minus z plus 1 into derivative of the denominator with respect to z, which is 1. It is limit z tends to 0, z minus 3 minus of z plus 1, that is minus z minus 1 by z minus 3. Either simplifying or without simplifying, you can evaluate the limit. Since the numerator is so simple, you just evaluate it. It is limit minus 4 divided by z minus 3 the whole square. You put z equal to 0, so minus 4 by 9. Here the singularities are poles. While solving the equation z square minus z minus 2 equal to 0, you can see its solutions are 2 and minus 1. So we can say its poles are 2 and minus 1. See, it is a second degree equation and we have two solutions. And so we can say these two poles are simple poles. Let the function be f(z). Now, f(z) can be written as 2z plus 1 by z minus 2 into z plus 1. If alpha, beta are the solutions, then z minus alpha into z minus beta will be the corresponding factorization. So here z minus 2 and z plus 1. Here both poles are simple poles. So for evaluating the residue, we have to apply the first result, that is residue at a is equal to limit z tends to a z minus a into f(z). So residue of f at 2 is equal to limit z tends to 2 z minus 2 into f(z). Here f(z) is 2z plus 1 by z minus 2 into z plus 1. You make the cancellation here, and it is limit z tends to 2 to z plus 1 by z plus 1. You put z equal to 2. So the numerator is 5, denominator is 3. Next, for getting the residue of f at minus 1, limit z tends to minus 1, z minus a, here a is minus 1 into f(z). See, residue of f at a is limit z tends to a, z minus a. Here a is minus 1, z minus a is z minus minus 1. It will be z plus 1. Here f(z) is 2z plus 1 by z minus 2 into. Here we will substitute the given function in which its denominator must be in factorized form. Then only you can easily remove the common factor. And it is limit z tends to minus 1 to z plus 1 by z minus 2. You put z equal to minus 1. You can see it is minus 1 by minus 3. And it is 1 by 3. Next, consider the function e raised to z by z square minus 1. we can find its poles by solving z square minus 1 equal to 0, which implies you should be very careful while solving this equation. You can also use your calculator, that is z equal to plus or minus 1. So, poles of the given function are plus 1 and minus 1. Say since it is second degree, we have two solutions. Clearly both are simple poles. So the factorization of f z is e raised to z by z minus 1 into z plus 1. You remember, if alpha, beta are the poles, then corresponding factorization is z minus alpha into z minus beta, provided the coefficient of z squared is 1. If the coefficient of z squared is a constant k, then its factorization is k into z minus alpha into z minus beta. Here, both poles are simple poles, so we have to apply the first result only. Residue of f at 1 is equal to limit z tends to 1, z minus 1 into f z. That is, limit z tends to 1, z minus 1 into e raised to z by z minus 1 into z plus 1. We cancel. It is limit z tends to 1, e raised to z by it is limit z tends to minus 1, z minus minus 1, f z e raised to z by z minus 1 into z plus 1. See, this is z plus 1, this will cancel with this is z plus 1. So it is limit z tends to minus 1, e raised to z by z minus 1. You put z equal to minus 1, then e raised to minus 1 by minus 2. That is 1 by minus 2e. Next, consider the function e raised to z by z square plus 1. You can find its poles by solving z square plus 1 equal to 0. That is z square equal to minus 1. So z equal to plus or minus root to minus 1. That is z equal to plus or minus root to minus 1 is I. So the poles are I and minus I. Clearly, poles of the given function are I and minus I. Both are simple poles. Now, f z can be written as z plus I into z minus I. Residue of f at I is equal to limit z tends to I, z minus I into f z. That is, limit z tends to I, z minus I into f z is e raised to z by z minus I into z plus I. That is, limit z tends to I, e raised to z by z plus I. You put z equal to I. So, numerator is e raised to I, denominator is 2i. See, this is the residue. Usually, we keep I in the numerator. So, you can write it as minus I e raised to I by 2. Really, it's not necessary, but our convenient way of writing is like this. Again, residue of f at minus I is limit z tends to minus I, z minus minus I into f z. F z is e raised to z by z plus I into z minus I. It is limit z tends to minus I, e raised to z by z plus I. You put z equal to minus I. So e raised to minus I divided by minus 2y. Conveniently, you take I to the numerator. So we know 1 by I is minus I. So 1 by I is minus I, so it will become I e raised to minus I by 2. I e raised to minus I by